Science.
Okay, thanks very much for introduction. Good morning, everyone. Thanks very much for coming to this presentation. My name is Zhiguo Zhang, and I'm from Shenzhen University. Well, actually, the speaker, Dr. Huang Gan, cannot be here because of personal reasons, so I come here instead. Today, I'm going to introduce our recent study on a EEG-based neurofeedback system. Maybe this talk does not fit the scope of this session very much, but I don't know why it is included here. Anyway, let's carry on. I will try to make my presentation short and interesting. Well, so it is the background of neurofeedback. Normally, we record the brain signals, EEG or functional MRI, and then we analyze the brain signals, EEG, to extract some useful features like band-limited power at specific frequency bands. Then we show the EEG features on the computer screen to provide a feedback signal to users. Then the users can regulate their brain activities according to the feedback. It forms a closed loop. Neurofeedback has found many applications, for example, in the treatment of ADHD. It can also be used for treatment of other diseases like autism, dementia, schizophrenia, and many others. However, the effectiveness of neurofeedback is still very controversial. Many people think that neurofeedback does not work for at least a certain proportion of users. And here, of course, there are many reasons contributing to the problem of neurofeedback inefficacy. And one important reason is that it's difficult to regulate our brain activities by ourselves. For example, if I let you increase or decrease your alpha wave, do you know how to do that? Yeah, it is not easy, right? So self-regulation of EEG is not easy. So it motivated us to develop a new neurofeedback system. In this system, we can use external sensory stimulation to change the brain activity, to regulate the brain activity. Okay, maybe you say it's not new, because everybody knows that external stimulation will change the brain activity, right? But here, the key point is that in our proposed system, the external stimuli are not pre-specified. They are generated based on our ongoing EEG. That is to say, we will decode our EEG activity in real-time manner, and then the information will be used to guide the generation of external stimulation. And now, let me use this example to explain our idea. We can simplify the alpha oscillation, EEG alpha oscillation, as a motion trajectory of a simple pendulum. If there's no any resistance, we can see that the motion, we can see from figure A that the motion trajectory of the pendulum is a sine wave, right? But if we exert a force on the pendulum at a specific phase, the magnitude as well as the frequency of the pendulum will be changed, depending on the phase of the pendulum at which the force is exerted. Right? This is a very simple example, but I hope you can understand our basic idea based on this. And actually, this is a paper published around 20 years ago. Researchers have already reported this phenomenon. The visual evoked potential are actually related to the phase of pre-stimulus ongoing alpha wave. Okay, due to time limitation, I will not go into the details. And let's see the system design. So we have, in the proposed externally regulated neurofeedback system, ERNF system, it has 4 modules. In the first module, we will record EEG. And then in the second module, we will decode the alpha phase. In the third module, we will generate the sequence of visual stimulation based on the decoded phase. And in the fourth module, we will deliver visual stimulation using LED. And now I will introduce these 4 modules one by one. The first module is very simple. We just record EEG. We can only record EEG only from one channel, OZ channel. And then in the second part, we will decode the phase of alpha wave in a real-time manner. And here we use C++ for programming, and we firstly design a bandpass filter to separate alpha wave, and then we detect the upward zero crossing point. These points are corresponding to the alpha phase at 1.5 pi. In the third module, we will generate the sequence of visual stimuli, and this visual stimuli should be delivered at one fixed specific phase. And from the example of the pendulum, we know that effect should depend on the alpha phase when a visual stimulus is perceived. So we examine the modulation effects when the modulation effects at a series of alpha phases. And if the system can really modulate the alpha magnitude, then the modulation effect should come out in a periodic pattern, and the frequency of the modulation function should be the same as the alpha wave. In the fourth module, we deliver visual stimulation using LED. And this is the experiment design. We recruit 20 subjects, and each subject did the experiment for twice because we want to check the within subject reproducibility of the system. One experiment has 2 parts. Part 1 is used for calibration. It means that in this calibration part, we record the resting state EEG and the visual evoked potential to determine 2 important parameters in the system. These 2 parameters are alpha peak frequency and the light intensity of LED. And then in the second part, evaluation, we did the new neurofeedback paradigm in 6 sessions. We also recorded steady state visual evoked potential for comparison, which will be introduced later. I will skip many technical details, and let's see the results. And here, in Fig A, the red curve and the blue curve respectively denote the maximal and the minimal modulation effect. We can see that the red, in the time range from time 0 to 20 seconds, the red curve shows that the Y coordination is alpha power. We can see that alpha power can be significantly increased by the technique. And on the contrary, the blue curve shows that alpha wave can be suppressed by our technique. So actually, as I said, the modulation effect depends on the phases. So Figure B shows the function which describes the relationship between alpha power and the different phases. We can see that it also has a periodic pattern. We also did time frequency analysis. We show that in Figure C, we show that not only the magnitude of alpha wave, but also the frequency of alpha wave could be changed by our technique. In other words, this new neurofeedback technique can arbitrarily increase or decrease the magnitude and the frequency of our alpha wave. Okay, this is from one subject in one experiment. In the group level, we can see the modulation effect is more significant. And actually, the modulation effect can be observed from all subjects in all experiments. The results are consistently good. And the frequency of the modulation function is significantly correlated with subjects, with the users' alpha peak frequency. And now we compare the new modulation method with some other methods. Here, the blue and red dots denote the maximal and the minimal modulation effects of the proposed system. And the yellow dots denote the alpha power in the resting state. We can see that the alpha power of the blue dots are higher than the resting state EEG, the yellow dots. And the red dots, which denote the modulation, denotes the alpha power in the minimal alpha power of the minimal modulation effects of the proposed system. That is to say, our system can arbitrarily increase or decrease alpha power. For comparison, we also include the purple dots, which are the alpha wave in a SSVEP paradigm. SSVEP stands for steady state visual evoked potential. It means that if we deliver visual stimulation at a specific frequency to subject, the subject will generate oscillation with the same frequency as the visual stimulation. We can see that SSVP can also modulate the alpha wave, but it can only increase the alpha wave. It cannot decrease the alpha wave. And also, you can notice that the blue dots are higher than the purple dots, which means that our method, which is an adaptive method, could achieve better modulation effect than the conventional SSVP paradigm. And we also compare our method with some other traditional neuromodulation methods. And I will skip the details. I just compare our method with the traditional self-regulated neurofeedback. Our new protocol has very good performance for all users because it does not require the users to learn how to regulate brain activities by themselves. And another important advantage of the method is that we do not need training. Yeah, because in conventional neurofeedback paradigm, subjects have to be trained for a long time to learn how to self-regulate their brain activities. But of course, it's just a very preliminary study. There are a lot of things to do. For example, we need to use a more complex mathematical model to describe the alpha behaviors. And more importantly, we need to check whether our system can modulate cognitive and behavioral states. Now, it is a summary. Here, we propose a new externally regulated neurofeedback protocol. And the best aspect of the system is that it can achieve very stable and consistent modulation effect for all subjects without any training. So this is our group and the grant I got to support this study. Thanks very much for your attention. Thank you.